is let's go ahead and add the name of this pigment. This is a chlorophyll molecule. Chlorophyll molecule. And chlorophyll molecules absorb light. So there's the sun. But instead of saying light from the paper that you had just copied down, you would say actually that it's a photon that's coming down. So photons, high energy packets of light, are striking the chlorophyll molecule. Sitting on that chlorophyll molecule are electrons, negatively charged subatomic particles. Right? And now, what would happen if you were to feed energy to an electron? What would the electron do? Sit there? It would have to move, right? Yeah. Whenever you have energy coming in, hitting an electron, it's going to push that electron to a higher energy state. So you could expect the electron to become excited. It moves to a high energy state. So over here we have high energy, over here we have low energy. How did the electron get way up there? Because of the photons. The photons made this possible. Now your electron's high up, having tons of energy. Now, if you throw a ball up in the air, that ball has energy once it reaches its maximum height, correct? And where did that energy come from? You, right? That was your arm, right? And so when it reaches its maximum height, well, it's going to fall back down, correct? Unless someone could be up in the air and catch it. No, yes, I'm saying yes, they could. So there's got to be a system that can grab those electrons and send them somewhere else. And we'll talk about that in just a second.
So the electron thing is the little squiggly lines going there?
This is the photon.
Not that, the other one.
This one? Yeah, this is the electron being passed down.
Okay.
Now, once you've done that, your electron is going to end up somewhere over here. And keep in mind, this is kind of the same electron that you began with here. So here it is at this location, and it goes up, and it goes over there. So describe at the end of this reaction, what's going on here? Is there anything left?
Yeah, it comes right back, doesn't it?
Nope, the electron's passed off.
Oh.
So now this is an empty space. Right?
Oh, and those electrons make food for it.
Sitting right here should be another electron, right? And you see the squiggly line again. So what's coming in? So there's a photon coming in there. And there's another photon coming in there. And what do photons do to the electrons? Excite them to a higher energy state. So in green, I'll show you the movement the electrons make to a higher energy state.
What's that black thing?
What's that black thing?
The dot, the circle.
This?
Yeah.
We'll talk about that in just a little while. Pushes up your electrons to a higher energy state, right? So there's your electrons up there. Now instead of them just falling straight down, remember they're caught by something. We talked about that earlier. How they were caught by a system. Let's call this a primary acceptor. This is also a primary acceptor. So a primary acceptor can take in excited electrons that were excited because a photon struck a chlorophyll molecule. Now you'll notice that the electron is then carried by a series of proteins. What do we call a system of electron carry stuff? Okay, perfect. So you have an electron transport chain that runs all through here, carrying the electrons to this location. And what happens when they get here? They're re-excited, correct? Excuse me. Picked up again by another primary acceptor, carried by a second electron transport chain, so they reach this spot right here. So how many times are the electrons excited? Twice, by two different photons. But remember that we could trace a single electron. We could name it, like let's call this electron Pete. Electron Pete starts here and ends here. So electron Pete is at this position at the very end, and there would be a blank spot here, correct? Remember how we said that we would need to replenish the electrons, right? So in cell respiration, what was the final electron acceptor? Oxygen, right? Oxygen was the final electron acceptor, and it produced what? H2O, perfect. So in the H2O are my electrons, right? Where did I get those electrons from? Where were they from? From glucose, right? As we broke down glucose and went down the steps, you pulled off the electrons. And then you put them in water, or oxygen, to form water. Now we need them back. So what do we have to break down to replenish the electrons? So I'm going to break down some H2O. I'm going to push in my electrons. That's going to produce H plus and O2. See, that's why I don't like drawing on the black circle, because you can't see it at all. You produce H plus and you produce O2. We know plants produce oxygen, right? Yes, that's how we're able to breathe. So, click. If you don't water the grass, what happens to it? So you know why you need water. So you know that the water and oxygen are directly connected. And so the difference here is the H's and the electrons, and now you know why the electrons are there. And the H pluses we'll discern. We'll do something with them in just a little while. We cool with this? Now the only thing I really haven't described, the only thing that I haven't been specific about, is really naming these systems. You have a system that takes in light and excites electrons. So I'm going to think of a nice, cute little name for it. Got it. Photosystem. And here's another photosystem. The problem, though, is that you can't name them the same, of course, because they're not identical, because they don't have the same energy. Do you see how the y-axis was energy? It's pretty discernible that this second photosystem is higher in energy, right? Cool. This is photosystem 2. This is photosystem 1.
Wait a minute.
Yep. They're numbered backwards. All based on timeline of discovery. Photosystem 2 occurs before photosystem 1. Which is higher in energy, photosystem 1 or photosystem 2? Photosystem 1 is higher in energy. And also, the chlorophyll here is known as P680, as opposed to this chlorophyll here that's referred to as P700. Now those numbers go in order. What does the 680 mean? That's the nanometers. That's the wavelength of light that's best absorbed. 700 nanometers, the wavelength of light that is best absorbed. This next picture is kind of cute, I think. You've got little people.
We have to draw this stuff?
No, I wouldn't draw this. Someone actually asked earlier, this is a funny story. He said, Mr. Fields, are there really little people, this is a true story, are there really little people inside the chloroplast? They're doing this. I said, wow. Because I don't know how to respond to that type of a question. Because obviously there's not. At any rate, you see that this object is excited to a higher energy state, passed off, then re-excited. So what does that mean this little ball is going to be? Okay, so this is representing the electrons. Do you see how the electrons are passed off to through this system right here? You've got an electron transport chain. And do you see how the electrons end up being accepted by two different individuals? So what does that make them? Primary acceptors. And you see how the electron is put into this container, this bank? So what are you making? Very good, NADPH. This appears to be higher in energy over here. This is photosystem 1. This is photosystem 2. PS2, PS1. Not the arcade console, the real thing. Good. You see how the electrons are getting excited in two different instances? Okay, so let's review this again. Let's back up a little bit. We've only got a little bit of time. This carries electrons, right?
Yeah.
What do we have here? We have photosystem 2, then photosystem 1, right? Because 2 comes before 1. This carries the electrons over here. How do you replenish the electrons? You get them from where? You get them from H2O. When you do that, you end up with excess O2 that goes out. That's no problem. That's what we breathe in, so that's all good stuff. How about all these H's? Well, that's a problem that builds up. Have you seen a buildup of H's occur before?
Oh, yes.
Okay, now let me show you one other thing. There's also some H pluses on the outside. And you see how this electron moves in this way? What does that do to those H's? It's going to drive them inside because the H positives are attracted to the electrons. So as the electrons get excited, they kind of help to pull in more H's. So what does this mean? You have a lot of H plus inside. And like anything else, it wants to pop. Can't pop though, but at least there's a doorway. This is the doorway, correct? What's the name of this enzyme that acts as a doorway for H plus? So you have ATP synthase here. And this works because you have created, again, an electrochemical gradient. And the H pluses fall through this gradient. Correct? And that causes the generation, the production of ATP from ADP and inorganic phosphate. Right? Now some people would be like, well, what happens to all of the H plus that's now on the outside if you generate all this ATP? Well, the H plus joins up with your electrons, and as you take NADP, NADPH is produced. And you know to produce NADPH from NADP, you're going to need yes electrons, but also yes H pluses. If you think about it, it's actually kind of unique to see how the system like all interconnects. Where did those electrons come from? Water. Where the H's come from? And they went their separate ways because light caused them to go their separate ways. Did they end up together though? On the NADPH. So you've produced a couple things here. You've produced some oxygen, which is great. Some ATP, which is great. And some NADPH. Those two items